Yeah, thanks. So let's start the afternoon session by jumping right in the middle of actually number 3 of the lectures. Number 4 is Pheno applications. So if you don't make it to the end, which is quite to be expected, you can also look into it on your own, because it's mostly plots and explaining the application of the stuff we actually still have to learn to some extent here and now. So the next point I wanted to focus on was photon radiation, and I talked to you already about this in this or another occasion, because this is a source of very distinctive effects of electroweak corrections. They are typically very large in some circumstances, and this I would like to explain a little bit better. So the reason why photon radiation induces such large corrections is, I would say, twofold. Let's look into this picture, and already in the picture you see kinematically, or it is indicated what one source of this specific enhancement of this type of corrections really is, and this is this kind of forward scattering of photons. So there is a collinear enhancement, in the sense that if you include all the photons that are radiated here within a collinear cone around, for example, this outgoing lepton, then a mass singularity builds up, which means if you calculate the same thing here with a massless electron, which is kind of motivated, if you just look into energy scales, you will end up with divergences that do not go away. So this is the situation when you are just, for example, calculating the photon radiation for a lepton, that you assume that can be isolated from basically everything, like a muon. A muon is almost such a particle because it is detected in the outer layer of a detector in these muon chambers, and most of the photons, they are just dumped in the electromagnetic calorimeter in the inner part of the detector. So assuming that you can isolate these photons from the lepton, as I've said, a mass singularity builds up, which means, just jumping in the middle of this formula here, that in this integration kernel, which describes exactly the collinear part of this radiation, you see this log of a lepton mass coming up. This is just part of the whole corrections, just to say that at the very beginning, you normally cannot isolate this radiation part, virtual plus soft, or so, from the rest of electroweak corrections. You have to take great care if you want to take things apart. But the collinear part, in particular, the one that has this logarithmic enhancement, is a universal piece of the correction that does not care about the nature of the process that actually produces this kind of lepton. And this is the reason why you can write down this effect in this factorized form, factorized in the sense that you have the radiation part factorized from a hard cross section. There's still some integration involved, but still differentially this kind of factorizes here. The theta cut is just kind of a measurement functions that are introduced here, which might, for example, cut into the picture here in the sense that depending on your experimental selection cuts, the lepton might be accepted or not, and the photon radiation might influence this, because if the photon takes away too much energy, maybe the lepton is too low energetic to be detected. So this should explain actually this so-called leading log final state radiation formula here. So I told you that this log survives if you assume perfect isolation. But just looking into the formula, you also see there is this kind of plus distribution that you hopefully will remember from introductory courses in QFT or QCT. This actually has the feature that if you integrate the whole thing over the whole range in this energy sharing variable set or splitting variable set, then this integrates to 0 by definition. And this is just the KLN theorem at work, which means that in this case, if you integrate over all possible ways the lepton is emitting a truly collinear photon, then the variable Z is controlling the energy fraction that is left in the lepton. And in the leading kinematics, basically, the momentum of the lepton, at least in this part of the calculation, can be taken as a light-like momentum, and the photon, of course, collinearly is also a light-like momentum, or represented by it. And you can split each light-like momentum into two collinear momenta, light-like momentum, in any way you like, just by rescaling, because a light-like momentum stays light-like if you just rescale it by any factor. And this is the set, actually, that giving you the possibility to share or to distribute the full momentum of the initial lepton into a photon and electron momentum in any way you like. And the KLN theorem is telling you that all kind of singularities in any kind of observable will drop out if the observable is defined in a, let's call it, sufficiently inclusive way. And inclusive means in terms of energy flow. This means if you, for example, in this collinear situation where the singularity wants to build up, if you include over all energy degenerate configurations, the singularity has to go away. That means if you integrate over the full range of this energy sharing variable, it has to integrate away. And this is what you see here. So this can also be exploited in this or another way to design appropriate observables. In a way, if you think about gluons and quarks, this is exactly what you do when you define a jet. Jets are defined in such a way that they are sufficiently inclusive that all the singularities that I want to build up in QCD cancel. Infrared safety, that's what Lance also explained in his lecture. And you basically have a similar situation here, but with a distinction that, in contrast to a quark, a lepton in principle can be detected as a lepton. So in order to make these corrections that might be very large because of this logarithmic enhancement, in order to make them smaller, to have a more stable prediction, you can, for example, what we call dress a lepton by collinear photons that come sufficiently close to the lepton. For the muon, this is not strictly necessary. In principle, you could do it. But for the electron, in a way, you have to do it because the electron is detected in the electromagnetic calorimeter, like the photon. So in either case, you just see some kind of shower in this calorimeter. And at the basis of just single events, you cannot not always say, is it really to 100% a photon or a lepton or an electron that went in there? On a statistical basis, you can, because of some patterns that typically build up in this showering, but you cannot say it really for sure in all the cases. So what you have to do, and you cannot, in particular, you cannot strip away Bremsstrahlung photons from the electron. So to really have a reasonable description of electrons showering in the electromagnetic calorimeter, you have to do this kind of dressing. And if this happens, then of course the logarithmic piece goes away here. And what in essence really happens is in your prediction that the large log of the mass ratio here is more or less a log of your cone size. This will kind of press down the impact of these corrections. So let's look into examples where this really manifests itself. Let's look, for example, into this example. What is it? It is Drell-Yan production of lepton pairs at a hadron collider. And you see here the invariant mass distribution of this lepton pair. And of course, at about 90 GeV, you see the C boson mass pole, the resonance. The relative corrections to this distribution is shown downstairs here, delta in percent. And what do we see? We see really a very distinctive pattern of corrections. It's not something that looks simply uniformly. So there are really interesting features coming in. Let's look first into the red curve here, which is scaled down by a factor of 10, which means the 8 here means here you have an 80% correction. This is quite a lot, because I told you, if you just look into the typical coupling strength, which is giving you an idea about the size of a correction for electric corrections, you would expect something at the percent level or so. You have 80% here. And this is exactly due to this logarithmic enhancement, coming basically from this convolution with this kernel. So can you understand the pattern here? Well, actually, I think yes, you can. We saw already a similar pattern arising for a plus and minus going to lepton pair, where I argued that you should have a large positive corrections to the right of the resonance. This is not what you see here. You see the opposite. You see a large positive corrections to the left. So what is the difference? You have an idea? The difference is what we actually draw here on the horizontal axis. For A plus and minus, we had the incoming scattering energy. And if you had more, you could radiate away a little bit of energy to come back to the resonance. But here you have what you reconstruct from the final state. That means, for example, in this factorization picture, that the lepton is first produced and then collinearly radiates off. You produce basically most of the time an almost resonant C boson, and then it decays into a lepton-antilepton pair. And these outgoing leptons, they radiate away a little bit of their energy, which means most of the lepton pairs have a center of mass energy close to the C boson, which is actually the source of this peak. And then they start to radiate away energy. So the energy that they finally have in the detection misses a little bit of photonic energy that was radiated away. And this is the reason why, from the resonance here, a lot of events are shifted to the left with lower invariant mass. That's the reason why the radiative tail here is on the other side. And it's big, as you say. And the reason why it's so big is the fact that I normalize here to the lowest order cross-section, which is off resonance. I have plenty of events on resonance. They radiate energy away and show up below resonance. That's the reason why so a huge correction builds up here. And this is just one photon radiation. And of course, you also have to include multi-photon radiation to really account for the experimental accuracy that you have here. So that's just the red curve. What else do we have here? Let me just look here. You can hardly see it because the line width is a bit small. There's a green dashed curve here. And you see here, the red curve was just for muons without any dressing. And if you do this recombination, as I've said, when the photons become too close to let's say the muon or whatever fermion, then I just add the corresponding momenta and I treat the lepton as a quasi-lepton, which has some kind of photon cloud surrounding it inside a cone. And then you get this green curve, and with the resolution parameter chosen here, it basically reduces the impact of this correction by a factor of 2. And if you just play with a number, this is exactly what I already indicated earlier. The large log of this mass ratio is here just replaced by the log of this resolution parameter. Typically, what people take is an R separation, and 0.1 or so is a good number for that. So you see that this dressed lepton curve has much smaller corrections, but still huge on the normal standard of electroweak corrections. So just to complete the picture here, what else do we have? There's a dotted blue line here. These are the truly weak correction. In this process here, you can separate the photonic corrections from the weak corrections. This has to do with the fact that this is a neutral current process without a W boson in leading order. If I had a W boson here, I could not simply treat the photons separately. The reason is that the W also couples to the photon, and if you just kind of add everything together to furnish a truly gauge invariant correction, I basically need the whole correction, almost up to details. But here, actually, I can just switch on first electromagnetism, all the photonic couplings, and in principle, I could also separate initial and final state radiation because the relative charges of leptons are more or less a free parameter in the model. Okay, I can separate photonic corrections and the rest of the weak corrections, this line here, that's something really at the percent level. So as expected. Yeah, there's also the QCD correction in there, scaled down by a factor of 100. I think it's around 30–40% if you blow it up by this number. So this is very typical for final state radiation. Just to show you again what happens if you have something with a definite incoming energy. Here is yet another example for the situation with initial state radiation, where I have these huge corrections building up to the right of the resonance. So this is something like E plus E minus to fermion pair. In detail, actually, this is for muon pair production, by the way. Yeah, here we have it. And just to prove that it's really this radiative return that makes here the correction so large, I show here two versions for the correction, namely the red one, which is just inclusively integrating over everything, and the dashed black one here has an additional cut at work. It should be quoted somewhere here. Yeah, this is a cut where I only allow about 10 GeV to be taken away by initial state radiation, and I can do this by saying that the difference between the center of mass energy square root of S minus the invariant mass of the final state can at most be 10 GeV, which means if I have, for example, here an energy of 125 or so, I can only radiate away 10 GeV in energy. I cannot return to the resonance. And you see, in the vicinity of the resonance, with and without this kind of cut, I get the same result. But if I'm above resonance by more than 10 GeV, basically the correction gets killed almost completely. Which is really telling you it's the initial state radiation with a radiative return that causes this correction here so large, it's about a 100% correction. So again, huge enhancement factors just by this photon radiation. I think we can keep it like that. Are there still any questions to this photonic corrections? Now, I should also add, I did not really refer to all what I have written down here on the slides. This universal piece that is ruled by this, or driven high by this lock of the lepton masses. These locks, they are known to higher loop order, even to 5 loop order. But this concerns only this universal piece which drives the effect so high. All the subleading terms, at some point, of course, they become highly process dependent. But to further improve on any full NLO corrections, it's good to know the leading pieces beyond, for example, NLO. Okay, maybe about this picture here, you might wonder what this peak here really is. It is something like the Higgs boson resonance. It's from an old paper from 2002 on muon collider physics, and we did not yet know the Higgs boson mass, and our guess 115 was not so bad, actually. Okay, so that was all I wanted to tell you about this enhancement by collinear photon radiation. I also promised to say something about electric corrections at very high energies, and this means, sure. Yes, address the lepton, yeah. Okay. No, it means that I produce any kind of configuration in the final state, and I calculate the distance of a photon to all leptons, let's say, and distance, for example, with this R measure. Yeah, the difference in rapidity in Euclidean combination with the difference in azimuthal angle. And if it is very small, let's say smaller than 0.1, I say that the photon most likely was just this kind of final state radiation photon. And then I recombine them like in a chat algorithm, Yeah, I recombine them, which means I just add the momenta and say, this is not my original lepton anymore. It's a kind of a quasi-lepton. And if I do this with a very fine resolution, I have something like a jet-like lepton photon emission cone. Yeah, and this is called the dressed lepton. And yeah, they don't like it so much. Okay, but going into this direction means really opening a can of worms. But for the electrons, something like that you always have to do, because you do not really see just the electron as one track in this electromagnetic calorimeter. This is a bit fussy. Okay, maybe at the very end we make it to some pheno where this will show up again. Let's now, for the meantime, go to very high energies, namely energies in the TeV range. And in the TeV range, even the masses of the W and the Z bosons are supposed to be small. That means if you calculate, for example, electroweak corrections for this TeV-driven observables, you might get good approximations, for example, by going into a massless limit for the W and Z bosons, which does not mean that you can neglect them, because otherwise you get all kind of singularities back, which you could only cancel if you did some QCD-like calculations with jet-like observables. But you can still kind of kinematically or analytically try to isolate the leading pieces. And the leading pieces are all logarithmic. You see it here. This is actually, this is the leading corrections to fermionic 2-to-2 scattering. Let's focus on the first line here. Yeah, this is the leading log piece at the one loop level. And you see it has the structure of course, electroweak coupling. This is basically the G2 squared, what you have here, times the log squared of the W boson mass over S, or the other way around. Yeah, so the S is driven by TeV energies and MW is, well, 80 GeV. And just plugging in numbers, in particular because of this prefactor, which is also enhanced by a factor of 4 because of the weak mixing angle, you get typically 10, 20, 30% corrections. So this is a lot. And you know the energy reach of the TeV is not exactly 1 TeV, but for many processes, you can even go to several TeV. So this is a huge correction that builds up. And looking into the source of this correction, you find that this is a virtual correction, that it's due to such diagrams here, where you have soft or collinear exchange of W or Z bosons. Yeah, the difference between a W and a Z boson is kind of subleading, because 90 or 80 GeV is almost the same in this log. So the reason why it's a double log can be traced back to diagrams like this, that it is basically a soft exchange on top of a collinear enhancement. So there is a whole tower of logs building up. For example, if you have only, let's say, a W boson that is collinear to one of those lines, but still not yet soft, you get a single log. Which is also showing up, you see it here, they are also typically at the level of 10% or so. And what you also see is that it is not enough, for example, to take the leading piece in this TeV range. Everything is such that there is no clear hierarchy of corrections. They are all kind of large. They typically have also different signs in front. So what you have to do basically at the one loop level to get reasonable approximations, you have to do a full one loop calculation. This is just to show you the source of the large corrections. But there is, of course, the hope that if you're not able to do a full two-loop calculation, you might get a reasonable approximation just by collecting the first leading logarithmic corrections of two loop kinds. So the second line here is just showing you the analytic piece of the leading locks there. And this line basically looks like the square of the first one. Just looking into couplings, although the lock gets power of 4, then there are sub-leading and even further sub-leading locks, which go like alpha squared, log power 3, power 2, power 1. So you see that they become a bit smaller, but still you can never be sure that you have reasonable approximation unless you have calculated several of them. Okay, so this is just showing you where these corrections come from and how they analytically look like. And this pattern that they are so large, you will see in many, many observables in any kind of high energy tails of distributions for LHC observables. Actually, in lecture number 4, an hour or so, you will see plenty of examples of that. Yeah, but look, this is just some exercise here. If, for example, then increase S, at some point this will take over. This is what I said, you are kind of in the region where you see them coming up, becoming dominant, but you don't yet see the full hierarchy where from leading to next leading to next leading, you get really much smaller. Okay, so what actually is the difference of these large corrections to something similar that you would normally calculate in QCD? There are differences. First of all, the theorems that rule the cancellation of such singularities are exactly the same. KLN theorem is just ruling the conditions when these corrections actually have to add up to 0 somehow. It's a statement about the cancellation of singularities. And the question is, why doesn't it happen here? There are at least 2 distinctive differences. I told you already that the KLN theorem basically has the level of inclusiveness as the basic requirement when all this should compensate, all these corrections. So this means all energy degenerate situations should be added up, which means, for example, virtual and real corrections should be added up together, like in QED, for example, where the Bloch-Nozick theorem, which is a kind of a special case of this situation, rules that you have to add at least soft photon radiation to get rid of the infrared, soft infrared divergences. So something similar must actually be possible here. In fact, it is. So for example, to cancel these large corrections, which are all loop corrections, virtual corrections, you would have to add real W and Z radiation. Like you add real photon radiation. Then at least one of the requirements is fulfilled, that you have a chance that they get cancelled. You don't do this usually because we want to disentangle process classes as much as possible. So I would like to treat, for example, single W production differently, like W pair production or C boson pair production. I don't want to add everything up. I want to have more information in there. And this is the reason why actually typically in the observables that are analyzed by experimentalists, such corrections do not cancel away. There's a second requirement that is not yet fulfilled if you, for example, add in, for example, additional W boson production or so, and this means the level of inclusiveness with respect to the quantum numbers. I thought the level of inclusiveness that you have to achieve in order to combine everything that belongs to each other is kind of the energy flow, which means, for example, it's not enough to include here real W radiation. You have to include real Z radiation as well. So you have to blind yourself with respect to the quantum numbers that distinguish the particles. Also, if you think about fermions going out here, you also would have to add, for example, when you have charged leptons, you also have to add corresponding neutrino production processes. Or if you have quarks, you have to sum over all possible quark flavors. So you really have to reach a full level of inclusiveness with respect to the energy flow. This also concerns initial states. And at the latest, at this point, you have no chance at all in proton collisions, because a proton is basically up quarks, down quarks, and gluons plus, of course, more. But the problem is the PDFs are as they are. You cannot simply say, I take proton-proton collision and want to reach a level of inclusiveness there, because you never manage to have as many up quarks as you have down quarks. The proton made its choice. It's more up than down. So what you would have to do then is that, for example, you would have to add cross-sections of, let's say, neutron scattering as well and things like this. So this is never going to happen. Yeah, which means that whatever you do, even if you want to reach the level of inclusiveness to kill these corrections in order to make your predictions, your observable perturbatively more stable, you will never manage it completely for a hadron collider. Also for a plus and minus, you would have to add scattering of neutrinos to get rid of these corrections. Cannot do that experimentally. Also electron neutrino scattering should all be in then. So this means the effects you see here, of course, by changing the definition of observables, you will be able maybe to make them more stable rather than facing these large corrections if you assume isolation everywhere, but you will never get rid of them completely. Yeah, okay. Two reasons that I've explained. One is that these massive gauge bosons can be reconstructed at least to a high degree. Secondly, the non-abelian charges of the W and Z and also of the doublets in the fermion sector, they are open. Yeah, so not like in QCD. In QCD, everything is colorblind if you go to physical states. You always have to sum over color, but you don't have to sum over weak charges here. You cannot even. Okay, I think I also have some numbers. Oops. Yeah, first of all, a little bit of analytics. Let's look into the kinematics of a typical 2-to-2 scattering process. So that's an S channel, that's a T channel. And what these calculations assume, which I have indicated here by the logs, is that you're in the so-called Sudakov regime. And Sudakov regime means that the scalar product between all external lines here is big against, let's say, the W boson mass, which means for the 2-to-2 scattering that both S, the center of mass squared, center of mass energy squared, must be large, but also the T, and T is something, I've indicated it here, that goes, of course, with the center of mass energy squared times, yeah, here it is for a massless case, the sinus squared of the scattering angle divided by 2, which is not so important. But this means that in order to have T, or this actually it's the modulus of T, the absolute value, in order to have this big, the scattering angle must not be 0 or pi. That means forward and backward scattering is not the kinematic regime where these logs build up. You need finite angles. And you see it also in applications. For example, if you go to the high energy limit in distributions, if you, for example, for a 2-to-2 scattering process, you look into a transverse momentum spectrum, this means KT much larger than MW, which means if you follow the KT here, actually, this means that theta cannot be, or sinus theta cannot be 0. This means that S and T are naturally large. So the high energy tails in transverse momentum distributions, they really go to the Sudakov regime. And you will see these large corrections there. On the other hand, for example, if you go to an invariant mass spectrum, like, for example, the MLL in Brilliant production, which I've already shown you, then small t is still possible, because the MLL is basically, yeah, in first approximation, it is simply S. square root of S, the center of mass energy, the Platonic center of mass energy, irrespective of any angle. And so small t is still possible there, which means that typically high invariant mass tails in distributions are not fully dominated by the Sudakov regime. Let's look into it. Just collected some numbers for you in Brilliant production. Neutral current. This is PP to L plus L minus, basically. And here I look into such an invariant mass distribution in terms of numbers. Here I count in only invariant masses bigger than 50, 100, 200, blah, 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 2000 GeV. And let's look into the red line here. These are the relative corrections. Only the leading piece of the Sudakov, as I just get it by blindly inserting numbers in this log. And I would expect here in the TV range something like 15, 25% or so. But the full corrections that I get, actually it's the delta weak that counts, goes only up to 10 or so. Yeah, so this is off. Yeah, because it's not really in the right kinematic region in which I have calculated the 25%. So there's no Sudakov domination. This is a different regime, actually. I also have to take into account the possibility that T is not yet that big. Would be a different calculation. On the other hand, if I take, for example, charged current production, that means PP to a W boson going to a lepton neutrino, and I look into MTL, which is almost the same as KT. MT is just the invariant mass that builds up in the transverse plane. It's basically KT, what you see here in the 2x2 kinematics. Then I expect that I have a Sudakov domination, and in fact, the numbers are showing this, because if I evaluate just the log, I get again something like 20, even 30% here in a TV range. And these are two versions of the Electroweak corrections, once with photon recombination, once only, and I in fact get something at the 30% level. So you see, it depends on the observable at which you look in the high energy tail, whether you are in the Sudakov regime or not. Okay, I think we can just keep it like that. Okay. And I can come to the last part of this more technical lecture, which concerns the treatment of unstable particles in quantum field theory. And let me just start again from the beginning. You have seen similar considerations already in previous lectures. So let's look into corrections to a propagator. Yeah, GR again is a renormalized propagator. In diagrams, I get, of course, a lowest order propagator plus an insertion of a one particle irreducible piece, and this can be iterated. I get a geometric series, and the first two terms you see spelled out here. Geometrical series can be summed up. You get basically the stuff that you insert here, you get in the denominator. The result you get is just this one, which you have seen before. And you can do, of course, this resummation both for stable and unstable particles, but there's a big difference in the result. Not formally in the way it shows up here, but if you look into the details of the self-energy, there is one distinctive difference. And this is the question whether in the vicinity of the resonance here, this sigma builds up an imaginary part or not. Because if sigma does not build up an imaginary part, at some point you will find a zero here in the denominator, and the thing just blows up to infinity. This would happen for a stable particle. For an unstable particle, the sigma develops an imaginary part. There are also theoretical theorems that rule the sign of it, and you can, by spectral analysis, kind of set up some rules for all these situations. I will not go into details here, but the point is, for an unstable particle, you get an imaginary part here. So if you are in the vicinity of p squared is m squared, you have something that prevents you here to fall into a pole if you just have real kinematics. P squared real, M squared real. If there's something imaginary, you will never hit the pole. You will never go to infinity with the propagator. And this is the reason why really a resonance with the finite height of the peak builds up. So stable particles, the imaginary part near the pole is 0. Unstable particles, the imaginary part is not 0. In fact, you can show that the sign of the imaginary part here is positive. This basically comes from causality, which means, in essence, if you just look into the vicinity of the pole, you effectively have something that looks like a mass squared. And if I take the minus sign in there, or I extract it from here, you have a mass squared minus a small imaginary part, because the width typically for a reasonable particle is smaller than its mass. So the mass squared here, the location of the pole, let's say, is a complex quantity, which I can write as a real part, which plays the role of, let's say, the mass squared, and the imaginary part, which comes, you can connect it to the width of the particle by going into, for example, analysis with cut equations and stuff. I have no time to go into that, but it's basically the total width of the particle that shows up here. So let's analyze this a little bit more in detail, because we have already trained ourselves to look into higher order corrections. We looked into renormalization, for example, and you remember that I explained the appearance of a real part here in this renormalization equation. So this is linking what? M0 is our bare mass squared. This is the renormalized mass squared in this on-shell definition that we had this morning. And this real part of the self-energy, this plays the role basically of this delta M squared. We had this already. And the reason why this real part in this renormalization condition, you can read it like that, was included is that people were kind of scared to introduce complex masses for consistency reasons with unitarity, basically. And you can do that. And if you still do this kind of Dyson summation of the propagator, this leads, of course, to a reasonable parameterization of the resonance. So you have to make use of this renormalization equation when you expand your propagator around the resonance. Just this one here. I forgot the R. That was why I was stumbling. There should be an R here. So when you plug in the renormalized self-energy in the denominator, you basically get this equation. You still see the P squared minus M squared, which gets modified by this correction here, which looks like a wave function renormalization. What else? You have still the imaginary part, because nothing is done with it. You have it as it is, because the real part does not go into the redefinition, into the renormalization of the self-energy. And so if this P squared is near the M squared here, this looks like a resonance in the amplitude. And if you take the absolute value squared, it looks like a Breit-Wigner resonance. So this nicely describes the situation. It also makes contact with the relation between the imaginary part of a self-energy and the width of the resonance, which is the decay width of the particle. And if you just divide out this factor here, you basically put it here in the denominator, you can make the identification that mass times width in the on-shell scheme is the imaginary part at the pole location, at least next to linear order here, divided by this wave function normalization. So everything looks fine, and you even have one way, for example, to identify the width. So that's one way of doing it. You can also modify this relation here and say, okay, in principle, I would like at least to try out what happens if I don't introduce this real part, because maybe it's a good idea to define really the mass of an unstable particle directly from the pole location in the propagator. And this is a complex quantity. So just for the fun of it, let's introduce a complex mass squared for an unstable particle, which means in this renormalization condition, I just drop the real part and end up here. Yeah, I just didn't write any more M on shell scheme because a different scheme. I called it mu. It has nothing to do with the renormalization scale, something. It's just to have another letter. And mu squared here is just the complex mass for this unstable particle fulfilling this equation. Yeah, the denominator of a propagator should be 0 at this point. I can also insert this into this propagator structure. Again, this is actually GR here. And what I get is something that looks very similar to here. I still have in the vicinity of the resonance my p squared minus m squared, mu squared, which includes the imaginary part. But if you look into details, it's not exactly the same, because here I still have the untouched imaginary part of the full self-energy with the leading p squared behavior. And here I just have this multiplicative form here. So if you just look into the location of the pole, it looks almost the same, apart from the fact that the p squared behavior of the imaginary part is different, because here the leading imaginary part is just this constant, and here there is still a p squared behavior which competes with the one here. So it looks almost the same, but the role of the gamma here and the gamma there is not exactly the same. In fact, if you analyze this, including higher orders, what you see that to strict one loop order, there is not yet a difference, but at the two loop order, there is. In particular, you will find that this mu squared, in fact, is a gauge independent quantity. You can calculate it perturbatively from all your input, because it's defined by this equation involving loop corrections. If you do that, you find that the mu squared here is in fact a gauge independent quantity, because the pole location in a complex plane is a property of your scattering matrix. That's something deeply physical. But here with the real part, starting from the two loop order, you find gauge dependent contributions. And this kind of backfires if you make use of this definition here when you parameterize other observables like cross sections, which actually means that the complex mass that was not so much liked decades ago by theorists is the better choice, the cleaner choice theoretically. Unfortunately, at lab times, the red version, the on-shell mass was used to extract it from data. So let's work a little bit more on this, in how far this really matters in practice. Maybe I should not dwell on this too long. It's just comparing to the two renormalization schemes, the real on-shell scheme and the pole scheme. There is contact between the two, because I can just subtract the defining equations here, this from that, and the bare mass drops out, and this is what I got here. So this gives me a recipe how to translate the renormalized values in this scheme to the other one or the other way around. I can solve this equation here in terms of a perturbative expansion, separating one loop level, two loop level, everything. And what you will find here is just summarized in these formulas here. This means that the mass squared in this real on-shell scheme and the real part of the complex mass here, up to one loop order, they are the same. But here I have sigma times sigma. This is a two loop quantity. I see differences plus any higher order stuff. And similarly also for the width here. So it really matters in detail, at least theoretically, what kind of definition you use. And let's go one step further and also look into numbers. when you do the math with W and C bosons, you can make use of, let's say, this simplified picture of the imaginary part of a gauge boson self-energy. If you ignore fermion masses, at least the fermions that play a role in the decays, you get just a proportionality of the imaginary part with p squared, which simplifies a lot. So if you can just here insert these numbers, what you find is that the on-shell mass and this complex pole mass, they differ by a two-loop contribution that goes with gamma squared. And the width here, similarly, it's a gamma to power 3 because you basically have one gamma factor in the whole quantity. So at the two-loop level, there are these differences, and you can plug in numbers. For example, you get differences in the W boson mass by 28 MeV and differences in the C boson mass by even more than 30 MeV. And both are larger than the corresponding experimental accuracies. So this really matters. So when experimentalists do their fit to resonances, they have to tell you what kind of parameterization of resonance they use, because I think I made this explicit on the next slide. The on-shell value, this is basically what you get if you fit to a bright Wigner with a running width here, with this p squared here still showing up. And the pole value is what you get if you just use a fixed width in parameterizing the resonance. So they should tell you what they have done, because then you know how to use theoretically which mass actually you have to associate with the measured number. And this is not always done. So what traditionally is quoted by experiments is in fact this on-shell value, which is theoretically not as clean as this pole value. But the difference is really phenomenologically important. I think I can skip this more or less. This is just making contact between this running width parameterization and fixed width parameterization. The first version is basically what you get, or what is tied to the on-shell scheme. The second one, what is tied to this pole scheme. So this was all just about the definition of a mass and a width of an unstable particle. The next question is, how do I use this when I want to describe a full scattering process? Is it enough just to worry about my renormalization scheme? The answer is actually no. There is more to respect. In particular, gauge invariance is some kind of issue here. And before I go to details, let's have some preliminary remarks about this. So this issue of gauge invariance is something that really goes beyond just the definition of mass and width that I have discussed earlier. It's really beyond the question of parameterizing the resonance, because a resonance process in phase space also has, of course, a region that is dominated by the resonance, and basically the whole phase space, which also has non-resonant regions in there. So it's about really the consistency to calculate amplitudes basically everywhere in phase space, on resonance, in off-shell regions, and also in the transition regions between on and off-shell regions where you see the resonance just coming up. And what does it mean to respect gauge invariance in amplitude calculations? Basically two things. First of all, I was very brief in the first lecture about gauge fixing. There's this gauge parameter, for example, that comes with this gauge fixing functionals. Like in a covariant gauge, you have for a gauge field dA or so, you just add to a Lagrangian dA squared, and you can put any prefactor, typically a 1 over xi in front of it. And the xi is a gauge parameter, and all physical quantities that you calculate, they are not allowed to depend on this gauge parameter. If they do, you have made something wrong. Because fixing the gauge is a non-physical process that you do in your calculation. The physics should not care about it. So gauge parameter dependence should not show up. Unfortunately, it's not automatically guaranteed that if you have produced something that has no gauge parameter dependence, that it is physically correct. If you have produced something that depends on the gauge parameter, you know it cannot be physics. If you have produced something that does not depend on a gauge parameter with a proper cancellation, you have no guarantee that it is correct. Yeah, it just passes the basic requirement that gauge parameter dependencies should not appear. Okay, that's so, but this is one necessary requirement in predictions. The next is the validity of some internal consistency relations, namely ward identities. And this is a bit harder to explain. Yeah, what are these ward identities? Actually, these ward, or in more general terms, these Lyapunov-Taylor identities are consistency relations between different green functions. You know, it's not exactly the green function that produces the transition amplitude, but it's part of the green function. Yeah, these amplitudes in there. But in certain kinematical regions, now these ward identities for, let's say, parts of your whole amplitude, which again then goes again to green functions, there must be relations fulfilled. I will give you examples on that. You maybe heard about gauge cancellations. I told you at the very beginning that, for example, if you do not yet have the full standard model in a prediction, you might end up with cross sections that blow up in the high energy region because you miss cancellations that restore a decent high energy behavior. If you fiddle around with the consistency of your amplitude, it might happen that you destroy such cancellations that still, although your theory is good enough to produce a reasonable cross sections, maybe in your predictions you fail to do that because you have destroyed some consistency relation. And it is in fact the production of longitudinal gauge bosons, for example, that require such internal relations, and they are ruled by this ward identity between green functions. And the point is, you should do whatever you can not to destroy such relations. Yeah, okay, I will give you examples later on. So what this all is telling you is that you need really some consistent ways, let's say schemes, to introduce a width into your cross-section predictions or amplitude predictions in a very consistent way. That means you should not break gauge invariance relations. And you should also aim at having still next leading order accuracy everywhere in phase space. And this is a non-trivial combination of requirements here. Let's maybe go one step further and look into examples how to do this, and maybe also look how to do it in good and bad ways. So what very early was done was just to take as a guideline this modification of a propagator. On the left-hand side, you simply see this free propagator that is part of your perturbative machinery. And on the other hand, if you're close to a resonance, it's essential that you have this kind of width part in it. And what you can, of course, try is, well, whenever you have a resonance, I just add here by hand such a width part. And you can do this in various ways. You can just add I am gamma as a constant. That goes on the name constant or fixed width scheme. Scheme maybe is already overdoing it. You can also try to improve this because you know by theorems a bit of the behavior of your imaginary part here. For example, you know if k squared is negative, you will never have an imaginary part. That's a consequence of causality. So you might, for example, try to be a bit better than here, that you say, okay, I introduce this width here only if k squared is positive. This is a theta function. Comes closer to the behavior of a single propagator, but maybe it's doing some damage for the whole amplitude. This is exactly what will happen. You can even try to be more clever if you have, for example, W and Z bosons that become resonant, you can say, okay, I know actually the k-square dependence here, the gamma of k squared, and I told you earlier, if you just do the calculation, you basically find it's k squared. And I know that it doesn't show up for negative k squared. So I can, in principle, write down here the step function, theta function times a k squared. This is called a running width. The earlier version was a step width. So just to anticipate a little bit the result, if you then look in your result for amplitudes, what you will find is that none of the schemes really respects gauge invariance, and you will see traces of this. Actually, the constant width, which is the most simple version of it, and it is treating k squared smaller than 0 in the wrong way, still respects U1 gauge invariance, like, for example, electromagnetic gauge invariance, but it breaks SU2 gauge invariance. Mildly means that there are wrong terms in your final result, but it could be worse. Yeah, this is what's meant by mildly here. And worse means the other two versions here, in particular the last line here, the k squared here can do a lot of damage if you are really off resonance. The k squared here can punish you by large wrong effects. You will see it in numbers. Okay, so these were just early attempts. Sometimes with a constant width, you get reasonable results, but in general, you cannot rely on the results done here. So in order to improve on things like this, it's more than 20 years ago when we came up with this proposal, one can in principle proceed almost like here in a constant width approach by making use of the idea of taking complex masses everywhere. And in order to still have this gauge invariance relations intact, we proposed that we just use the complex masses consistently everywhere, even in couplings, for example, in the relation when you calculate the weak mixing angle from the mass ratio. We just proposed, okay, let's do it with the complex masses as well. And this has the benefit that all these gauge invariance relations in amplitudes, they look like algebraic relations. And algebraic relations kind of survive also a step if you interpret a real parameter as a complex parameter. If it is a truly algebraic relation, this will hold. Such relations can only break, for example, in this step of, let's say, analytically continuing something from a real to a complex parameter. This will only break if you have complex conjugation in the game, which is not the case in these gauge invariance relations. There are also consistency relations that have to do with complex conjugation, and these are so-called cut equations. This is the expression of unitarity. Unitarity in the sense that links different processes, by the way. So by doing this analytic continuation, you can interpret this in such a way, you will not break gauge invariance relations. Gauge parameters will still cancel, water identities are intact. And in fact, this is a workable scheme for any kind of lowest order prediction. This does not cause any problem. And it has also the major benefit, I will talk about this later, that you can generalize it to next to leading order, which we had done later actually. Okay, let's look into numbers. In papers that I've quoted, you find many more. Yeah, sure.
For me, is that this schema you cannot apply this when you do an analog unitarity or
Yeah, you could actually do that, but because unitarity methods, okay, what do you have to do? You would have to be careful with the complex couplings. When you do unitarity cuts and stuff, basically what you would have to do is to leave out the imaginary parts when you do unitarity cuts, things like this. Yeah, I would not go too much into details. It's my expectation. It's not a proof, but my expectation is that you could in principle do it as well, because the imaginary parts you kind of deal with in unitarity methods, They don't have exactly this quality. Okay, you have to be a bit careful if you do unitarity cuts. What you do actually is you replace a true propagator by something like a delta function of p squared minus m squared, which is at first sight causing trouble, of course, if the mass is complex. Okay, this is something I think nobody has yet done. Which has to do with the fact that these unitarity methods are not so much used in electroweak calculations. Yeah, because the whole problematic is kind of different. So let's stay with what we safely know. And let's look into this example. It is, let's say, multi-particle production, and here it's 6 fermion production in E plus E minus, which, for example, features gauge boson scattering, which nowadays is analyzed at the LHC in proto-proton collisions, also triple gauge boson production. So it's quite complicated. Here with 3 resonances, you have 2, so there are plenty of stuff that appears in one and the same phase space. And what I have depicted here in the table are cross-section predictions with rising energy up to the multi-TeV range, produced with some cuts. You can look it up in the paper. And you see, for example, that you get a reasonable high energy behavior even with a constant width, but not for the running width. You see, for the lowest energies, the problems are not yet building up, but in a TeV range, you get something at the order of 13,000. What is it? Picobarn, femtobarn, where you expect actually something like 26. So this blow up just comes from this wrong k-squared factor in the off-shell region. There are plenty of more such examples, but this is one with the highest multiplicities we have looked at. This is simply totally wrong. The complex mass scheme, for example, is just producing a very reasonable number, and in this case, as said, even the constant width is leading to a reasonable result. So why actually do you get into trouble with gauge invariance in the high energy region? I told you already this has to do with longitudinally polarized vector bosons. For example, here you can just look into the situation where you have one vector boson that decays into electron-antileptron pair, like for example here or there or here, there, and there. And this vector boson is still near its resonance. So, you know, if you could in principle calculate the cross-section also with a stable, supposed to be stable vector boson, and then you would very explicitly see that you have this longitudinal polarization vector building up with this weird high energy behavior, because the polarization vector of such a vector boson, the longitudinal polarization vector, looks like momentum k mu, let's say, over its mass. And the leading high energy behavior has to cancel away. Otherwise, you get punished with this unitarity violating terms. And this is also taking part when you include the decay here, because effectively here, this current here acts like a polarization vector. You see it here coming in. Now, there's a piece that goes with a k mu here from this current here. And this is actually mimicking a longitudinal polarization vector from here. And in order to produce a reasonable amplitude in a high energy behavior, this k mu, which is contracted with the rest of the diagram by this propagator here, a cancellation must happen. And this cancellation is ruled by a Ward identity, which is just written down here. That means the momentum contracted partial amplitude for this production process must be something like a mass times the corresponding partial amplitude for the corresponding pseudoscalar, would-be Goldstone boson amplitude here. Yeah, some people call this relation Goldstone boson equivalence theorem. And this is basically a consequence of this Ward identity. It's an SU2 Ward identity because you need it here for a massive vector boson V, which can be a W or a set. So this Ward identity turns here the bad high energy factor into a constant. And you must not destroy this relation. And this is, for example, destroyed in this line here, in the red line. Okay, just to show you what can go wrong. So I should make things a bit shorter, I guess. This was all actually very general, or in this example, at leading order. You also need width schemes for higher order calculations. And I would say there are basically two candidates that are successful. The one goes under the name pole scheme, and I only sketch the idea here. And the other one is exactly this complex mass scheme that I have explained in leading order. So what is this pole scheme about? Just very sketchy. You have any amplitude M, which has a resonance in there. So there is a part that is enhanced by resonance, and you have also diagrams which have no resonance. Yeah, and of course, there are many momenta in there, but I singled out only the momentum P going through the resonant propagator. So what you know, if you're sitting directly on the resonance, first of all, this blows up to infinity. You have to do something against this. But what you also know is that the residue basically is connected to the process that treats your resonance as a stable particle. So this means this is something like a consistent S matrix element. That means the residue R here at P squared is M squared is something that actually is a gauge independent quantity. So the trick now, or the proposal of this gentleman, was that you just play some add and subtract trick. Yeah, you basically turn this factor into something that has a constant residue, R of M squared instead of P squared. Of course, you do something wrong. And in order to repair the relation here, you just add back the difference. So this is a true identity here. Yeah, because this part with the R of M squared just is canceling out. But by writing it in this way, you see that very naively, you have something with a constant residue here, and this is actually non-resonant, because when you go with P squared to the vicinity of M squared, this ends up to produce a derivative without resonant enhancement. By the way, real life is more complicated than this idea for various reasons. So this is just rewriting this formula. And now the idea was, okay, I just include here in this gauge invariant piece, I include here this imaginary part from a Dyson summation, and I switch to the complex pole upstairs here, which is also, in a way, changing things. But the difference between this modified version and the original version is also something that you can kind of hide in the redefinition of this off-shell but non-resonant part. So you can also turn this actually into an identity by tweaking here the n into some n twinkle or so. So the overall idea and expectation was that this should be consistent and gauge invariant, because I modify only this gauge invariant part here. And it should also produce next to leading order everywhere, because I include corrections in the residue and also in the off-shell part. And in fact, in principle, it works, but it really becomes very complicated when you go to details. It's really subtle and cumbersome because of complex kinematics here, and the fact that actually here, this is not exactly only non-resonant, there are also non-analytic pieces coming from the resonance, which go under the name non-factorizable corrections. That means what you have here, if you do an expansion around a pole, this is not what mathematicians call a Laurent expansion around a pole, but it's a branch point. I hope you remember what a branch point is. It's, for example, in a logarithmic function, the 0 point. You have a branch cut ending there, which is not a pole. It's more complicated, and things like this happened here as well. So it's full of pitfalls, but sometimes you can formulate it. And I show an example, hopefully, at the end of the lecture, where we have used this definition as well. The whole thing here is nevertheless a basis for something simpler, namely what we call very often a pole approximation. which is a modest version of this, in the sense that you might say, okay, maybe I'm not interested in a next to leading order, a corrected prediction everywhere in phase space, but only near the resonance, because well, the major part of the cross section comes from there. Yeah, which means in practice that you basically only take this piece here, which has the resonance enhancement, plus maybe something that survives from here, which is these non-factorizable corrections. So this goes under the name pole approximation, or leading pole scheme, or whatever. So this was one early proposal, which turned out to be a bit more complicated than originally planned. And finally, I have already indicated this. There's this complex mass scheme, which you can really promote to a full next to leading order prescription by the idea of, again, taking the bare mass squared, let's say take here the W boson, splitting it into its complex version, plus again a normalization constant. So this is simply the same as we did before. We just don't take this real part in this consistency relation. And we accompany this complex mass normalization with the complex mass parameters, just with complex couplings coming again from this way of linking the weak mixing angle to the mass ratio. This just becomes complex. So what are the benefits in green here? Well, this is just the normal machinery you do. So perturbative calculations work as usual. There is no complicated shuffling of terms like here. It's just Feynman rules and applying them. There is also no double counting of contributions. You don't add or subtract something in your theory, because you just do normal renormalization, which is something like a reparametrization of one and the same theory. What else? Gauge invariance, this Lyapunov-Taylor identities, gauge parameter independence and stuff, it's all maintained because it looks like an analytic continuation in the mass parameter. And you have NLO accuracy everywhere in phase space. So that's all very nice. One should also be honest and look into points that maybe are not so trivial. First of all, there are so-called spurious imaginary terms, which, for example, come from this complex couplings. So actually, there should not be any width effect in the couplings, but nevertheless, you have it here. So if you use it, for example, in a lowest order prediction, you have effects of the relative strength width over mass, which is about 3% for the W and the Z, have in there. But already in a tree level calculation, leading order calculation, you see that this actually counts as a higher order effect, because width over mass is something like order alpha. And if you just follow the same logic here at next to leading order, you find that these spurious terms, they are of two-loop order. So in a way, because it's only a reparametrization of the whole prediction, the whole machinery repairs itself order by order. You do a leading order calculation, you have kind of spurious imaginary terms of next to leading order complexity. If you do everything at next to leading order like here, the spurious terms are of next to leading order. So this looks okay, but you have to make sure that there is no further blow up of these spurious terms, which could ruin your prediction. You saw something like this in this running width scheme. The width effects are always counted as higher order, but still they can be disastrously large if they are inconsistent. But this blow up of wrong terms only comes if you destroy consistency relations, namely this Ward or Lyapunov-Taylor identities, but they are intact. So there is no blow up mechanism of spurious terms. Okay, so that works. These nice features come at a price, which is was there, but it's paid the price, namely that you have to do your loop integrals always with internal complex masses. If you once have done this, even these one loop integrals, let's say a box integral with many scales with complex masses, you will see it's a pain. So in QCD this doesn't happen. There you have different difficulties, but The good news is actually all those one loop integrals are known with complex masses. You can in principle just take an appropriate library meanwhile for that. So what else should I say to this scheme? The unstable particles actually are only allowed as internal resonances. And sometimes people just want to have also an unstable particle as an external state to make the kinematics a bit easier whatsoever. You should not mix that. Yeah? If you really would like to take this consistently, you should really, whatever you can have as a resonance is an internal state, and the external particles, they should be really allowed as stable particles. And very finally, well, we expect that everything will also work at next linear order, but nobody has really worked this out. Huh? But this is already, well, ambitiously looking ahead. Okay, technical details. I can kind of skip this because this is just formulating the same thing as before in the real on-shell scheme, but you never will see any kind of real part operation in this stuff here. So just one example, almost close to the end. This is still lab physics, A plus and minus for fermions via a W boson pair. I have shown you, I think, in one of the previous lectures, a similar curve here, where lab data were compared with the predictions at the time. Meanwhile, after lab, it was around 2005, as you see here. We made the full 2-to-4 next to leading order calculation, was the first of this complexity, which is more precise than the lab treatment, which went under the name double pole approximation. This is one of these calculations that was done in this leading pole approximation. So this kind of blue band here is replaced by what goes under the name full here with this very narrow line here. There is no error indicated for that. The realistic precision of this line is something like, let's say, maybe 2 per mil or so, 3 per mil. And you see, it confirms the double pole approximation nicely. Yeah, basically here and here in the relative correction. You see also, the state-of-the-art calculation, the black line lies in this small width of this double pole approximation, unless you reach the vicinity of the threshold for W boson pairs, where the double pole approximation in the way we have formulated it at the time is not applicable. Yeah, so. Sorry? Intrinsic uncertainties, let's say, missing higher orders. Yeah, so yellow is the so-called improved Born approximation, which means only universal corrections. Meanwhile, you know a lot about this. Yeah? This is initial state radiation, a little bit of delta alpha and delta rho, and there's also a Coulomb singularity piece there. Yeah, so you end up here basically with a 2% uncertainty in yellow, which is not good enough to really describe data in the way you would like to have it. Yeah, it describes data, but well, you cannot make a difference. Does it fit or not? Yeah, and the blue band, this is, let's say, 0.5% accuracy. The double pole approximation you can associate with, let's say, 0.5% accuracy in this lab range here. Not close to threshold, but maybe starting from here. Yeah. And this full off-shell calculation also is valid below the threshold here. Yeah, as I've said, you have next to leading order accuracy everywhere. So we have 2 minutes for lecture number 4. No, just kidding. Let's at least go and look what we can do. I have to stop sharing here, I guess. And restart it. Yeah, we can at least look into the example of, oops, it's not what I wanted. Okay, I know why this happens. Again. Here we go. At least I can show you the application of all this for single W production and single Z production. So I skip kind of advertisement for precision. This was already shown in other lectures. And I just want to give you one or two results on single W and Z production. That means Strelian, which is important for reasons I've already explained, high precision measurements, effective weak mixing angle, W boson mass, and so on and so on. So just to entertain you with pictures, I also included event pictures from Atlas and CMS. Here, that's a typical W event. You see one muon going out to the muon chamber and missing transverse momentum indicated in light blue here, and basically nothing else. Here for a muon pair. And I have just given you a very brief list of precision calculations which were done over the last decades, culminating basically in the N-cube LO calculation for the full cross-section. On the QCD side, and of course at next to leading order, also electric corrections have been calculated. Doreen is also here. She also worked on this, which the results of which exist meanwhile for about 20 years, even a bit more. And most recently, the next to leading order pieces where you have crosstalk between Electroweak and QCD corrections were also taken care of. So see, this is a long list of calculations. Most of them here suppressed in the list of references, and there went a lot of effort in there, including also resumations, which is also part of one lecture series here. So let's maybe find a little bit of that again, what I have discussed on the more quantitative basis. Here you just find the result for the total cross-section, where actually the whole predictions are driven basically by QCD corrections. Let's go further on. Here you find a most recent result from CMS, but there's also Atlas results where the branching ratios of the W bosons have been reanalyzed with higher precision. There was kind of tension concerning lepton universality at lab times, and now the new results, which are colored here, they show nice agreement with the hypothesis of the standard model that all the leptons should more or less lead to equal branching ratios up to phase space effects. Okay, this is not yet where I wanted to go. These are central observables for W boson production and C boson production, including these kind of shapes, where in particular electric corrections will kick in at a significant level. Again, you see the C boson resonance, and here you see in the missing ET and in the MT distribution this kind of Jacobian shoulder from which the W boson is extracted from data. You should make up your mind why here the shoulder shows up at 80 GeV, here only at 40. Maybe it's too late for some questioning. Let's just look into typical results for corrections. This is for W boson, the MT distribution. Again, you see something like a radiative return. Above resonance, you see just kind of corrections of a normal size. On resonance, you radiate away actually your events. So you get a large negative corrections, and they show up as a lower tail here. If this is kind of the natural size of the electric corrections, you see just above this expectation, you have these larger corrections. It's much more washed out for hadron collider as compared to lepton colliders, but still you see the same kind of behavior here. And you see, of course, you have to take care of these next leading order corrections in all your predictions. And here, this is just a leading order exercise, drawing your attention to the level of precision you need, because this is just resulting from 3 different leading order predictions for this distribution, one with a central value of MW, and once in the black curve, I increased the W boson mass by 10 MeV, and in the other case, I reduced it by 10 MeV. And 10 MeV is basically the precision you aim at the LHC. The CDF people claimed they have already reached a precision of 9 MeV, which means to this level of precision, you have to predict this distribution, because this is the difference induced by a shift in the W boson mass at this level. And you see it's basically 0.5%. And if you want to exceed this precision, you have to predict the shape of the distributions at the per mil level. Yeah, this is a crazy accuracy actually. What else? These are the typical corrections, just skipping it. And here, for example, you see, and let me take this as a closing plot here. You see the corrections, the difference in the corrections, in relative corrections that I got when I compared two different schemes to introduce the width of the W boson. CMS is the complex mass scheme I advertised, and FS is yet something different, where I factorize this resonance structure from the corrections, or the corrections from the resonance structure. It's not exactly the pole scheme, but something in a similar spirit. And you see that this is 0.1%. So here we are in good shape, that the resonance handling is quite under control at the level we need it. And the level I just argued for here is this 0.1% level. So you find more in the slides. I leave it up to you to look into this. For example, you see similar results for C boson production. There's also more on di boson production. There's vector boson scattering in there, and a little bit of Higgs physics. This would have filled another lecture. So nevertheless, I hope you learned something, and maybe you are also encouraged to look into further applications. I will be here, so if you have questions also to the material not covered here explicitly, I'm happy to go into it in private discussions. So thanks a lot for your attention. Yeah, we have one here. Exactly. Well, one possibility is whenever you have kind of boson production, if you manage to do this, you can include the decays. And then you're again in business with a complex mass scheme, which means you have to calculate also a lot of junk from the off-shell contributions. Yeah. Let me press a button here and just scroll forward like hell. This is basically what you find here, for example, in vector boson scattering. So again, this sub-process, and what we and even more application came from a group of Ansgar Denner. Partially we worked together on this. Actually, one could imagine, I just want to have this vector boson scattering described, that I can kind of truncate the process here, and I'm happy with on-shell produced W bosons, but still, well, the machinery was also there to do that. You can calculate the full 2 to 6 process even at the 1 loop level meanwhile, and use the complex mass scheme, because then you have only stable particles in the final state. But well, in a recent paper we have shown actually that the off-shell pieces that you get also at next leading order accuracy in this complex mass scheme, actually they are not really needed. But this is a weird situation, because many years ago nobody would have dreamed about these 2 to 6 calculations at the full next leading order level. But meanwhile, because of this machinery of automated generators like regular open loops, to some extent also Mudgraph is going this direction, the amplitudes are not the showstopper anymore. So in a way, it is safer to do this monster calculation with really 10,000 of diagrams sometimes, rather than fiddling around with pole expansions here. And you know automatically, when you don't do a pole expansion, you know the off-shell tail is there. Yeah? You can rely on that. So that's one part of the question. Unless you are not running into other trouble, sometimes it's easier with the modern machinery to take into account the decay of the W boson rather than truncating the process there.